Hi there, and welcome to another lecture of CSE331. In today's video, we're going to continue our discussion on DFAs, Deterministic Finite Automata, and we're going to check out some more examples. The extended transition function is a function that takes two arguments just like the transition function. The first argument is a state, and the second one is a string. We sometimes represent the extended transition function with a hat over delta just to distinguish it from the transition function. Remember, the second argument of a transition function was a symbol, not a string. But for an extended transition function, the second argument is a string. We represent a string with a W here. The function also returns a state, just like our good old transition function. It tells you the state in which the automaton ends up in. If you start from state Q, which is given as the first parameter, and if it receives an input string W. The function can take in a string of 0 to any length. But if it's a string of length 1, it's just one symbol. And using delta hat in that case is kind of pointless, although it wouldn't be wrong. Let's take an example. What is the delta hat of Q0 and 1001101? Meaning, if we start from Q0 and we process this string here, where does the DFA end up? That's what we have to figure out. The first argument here is Q0, so that's where we're going to start. On the first symbol, which is 1, it goes to Q1. And on 0, we come back to Q0. The next symbol is 0, so we stay on Q0. The next symbol is 1, it moves to Q1. Again, we have another 1, so it moves to Q2. The last two symbols are 0 and 1, so following this loop transition, it stays on Q2. So the output of delta hat of Q0 and 1001101 is Q2. Also notice that the string contains two consecutive ones, so it clearly belongs in the language that we are working with here. So when the automaton processes the string, it should end up in the final state, which is Q2. And it did. Cool. That means it works. How about this string here? What would be the delta hat of Q1 and 01001? That means we're going to start from Q1 and process the string 01001 and figure out which state this DFA ends in. The definition of the extended transition function is an induction over the length of the string on which this function is applied. The basis is delta of Q and epsilon is Q. That means if you're in state Q and no input symbol arrives, we're going to stay in the state Q. The induction is, suppose the string is WA, where W is a string and A is the last symbol, and W concatenated with A is the second argument. And this inductive rule means to first calculate delta of Q and W, so the delta of Q and W here, which of course will give you a state. And then from this state, we have to calculate the delta of that output state of delta of Q and W and the last symbol A. Let's try and calculate the extended delta of Q0 and the string 110. The string 110 is WA in this representation. Q0 corresponds to Q, the first argument. Now we're going to have to break it down so that one part of the string is W and then the rest of the part is A. Definitely the last symbol would be A. So W is 1, and A is the last symbol, which is 0. To calculate delta of Q0 and 110, we have to first calculate the delta of Q0 and 11. And then we're going to have to break this part down further. And this is how we're going to do it. So delta of Q0 and 11, it's the same structure as this one, right? Where Q is Q0 and WA is 11. Here W is the first one and A is the last symbol, which is also a 1. To calculate this, according to this rule, the inductive rule, we first have to calculate delta of Q0 and 1. And then we're going to use the output of this function here as the first argument of this entire delta function. So after breaking it down to a single symbol, this is what we have. Now we're going to start calculating. We're going to calculate from the inside out delta of Q0 and 1. So from Q0 on seeing 1, we go to Q1. So we're going to replace this entire thing, delta of Q0 and 1, with Q1. And now we're going to have to calculate delta of Q1 and 1. From Q1, on seeing 1, we go to Q2. So delta of Q1 and 1 would be Q2. And then delta of Q2 and 0 gives us Q2. So that's how we can calculate using this induction rule. Now that we have a complete idea of how the transition function works and what it means, we can define the language of a DFA in terms of delta. The language of a DFA is a set that contains strings W such that delta of Q0, which is a start symbol, and W is a state that belongs to the set of final state, which we represent with F, capital F. The expression I'm using here is called the set former. It says the set L of A contains the strings W. Now L of A, of course, means the language of an automaton A. And we read the vertical bar as such that. And then we write the conditions or the description of the language after that vertical bar. So we can read it as W such that W belongs in the set of 0, 1, clean star, and you know what that means from regular expression, and W contains 2 consecutive ones. And this is how we can describe the language of our running example. Let's try and design some DFAs. We're going to start with substring problems, and we've already seen how to make a DFA that accepts strings that contain the substring 1, 1. Now, what if I wanted a DFA to accept strings that start with the substring 1, 1? So we're going to need a start state, and here we have it, Q0. Now, if the first symbol in the string is 0, then the condition that the string should start with 1, 1 is already violated. If the string starts with 0, it clearly doesn't start with 1, 1. So no matter what the rest of the symbols are, we already know that the string should be rejected. We don't need to check for anything else. So what we want to do is trap it in a non-accepting state Q1. And the DFA should stay here for the rest of the symbols of the string. So to do that, we put a loop transition here on state Q1, and the transition is on every single symbol of the alphabet, which is 1 and 0. It basically means that it doesn't matter what the next symbols are, it should stay trapped in this state. We actually call this state the trap state. A trap state it basically means that no matter what the next symbols are, once we're at this state, the string has already violated some condition to be a part of the language, and it should be rejected. That's why if the first symbol is 0, we just trap it. If the first symbol is 1, then we're on track. Maybe the string does start with 1, 1. So we move to state Q2. This state means that the string starts with 1, that the first symbol of the string was 1. If it wasn't, then there's no other way we could have gotten here. You can pause the video and think if there's actually any other way we could have gotten to the state Q2, even if the first symbol wasn't 1. There isn't. Now, when we're at the state Q2 and the next symbol is 0, that means the second symbol in the string is 0. The string starts with the substring 1, 0. Again, the condition is violated. So, we trap it. So on Q2, if the next symbol is 0, the transition should be to the trap state Q1. However, if we're at Q2 and if the next symbol is 1, then the string does start with the substring 1, 1. So we take it to the final state. And since the condition is fulfilled, the string should be accepted regardless of what the next symbols are. So we put a loop transition on the final state on both the symbols of the alphabet. You must have noticed how the trap state Q1 and the final state Q3 both have a loop transition for all of the symbols in the alphabet. What do you think is the difference between the state Q1 and Q3? What makes Q1 the trap state? Why am I not calling Q3 the trap state? Give it a thought. That's it for this video, and I'll see you in the next one.